The belief I want to take apart is that deep learning made regression obsolete. Let me admit my own bias first. Reach for the heaviest model in the room out of habit. And on real work, again and again, a first-year student could run beats me. That kept happening, so I went digging for why, and the answer changed how I pick models. Start with one artificial neuron. It takes your inputs, multiplies each by a weight, and adds them up and pushes the total through an S-shaped step that squashes it into a number between 0 and 1, a probability. That is it. That is the whole unit. Now leave the textbook, and most prediction in the world is not images or text. It is tables, rows, and columns. A customer, a balance, a late payment, a yes or no. Credit scoring, hospital risk scores, insurance pricing, the test your team ran on the website last week. On that kind of data, the simple family is hard to beat. A study from a few years back across 45 tables found that decision trees and their boosted versions, the very deep network, they tried on medium tables of around 10,000 rows and ran far faster doing it. So let me show you what the line is actually doing when it fits, because it is the same move a plumb line makes. Picture all your data as one tall point in a big space. The predictions your model can even make form a flat sheet through that space. The true answers almost never sit on that sheet. So fitting means finding the closest point on the sheet to the truth. And the closest point on a flat surface is always straight down at a right angle. Write that right angle condition down and it becomes one clean equation. In plain words, it says, pick the weights so the leftover error points straight out of the sheet, square to every column you feed in. That is the whole derivation. And because it is one equation, you solve it in a single shot, which is why a regression fits the time a deep network spends warming up. And this is not a metaphor. It is the same math physics uses. Hang a weight on a string beside a tabletop. The string finds the shortest path to the surface, straight down at a right angle. That is a projection. Least squares does the exact thing, just in more dimensions than you can picture. The shared object is the perpendicular. Closest point to a surface means drop a right angle onto it. Whether the surface is a tabletop in 3 dimensions or the sheet of all your models' possible predictions in 500. Same geometry, same answer. The statistics agree too. The weights that make the leftover error smallest are also the weights that make your data most likely if the noises follow a bell curve. There is a second reason the simple model holds up, and it is a dial every model sits on. Your prediction error breaks into 3 pieces. One is how far off your model is on average, what researchers call bias. Another is how much it twitches when the data shifts a little, called variance. The last is just plain random. You can never remove, just plain noise you can never remove. As you make a model more complex, the bias drops, but the variance climbs. Push too far, and the model starts memorizing the wiggles in your training set instead of the real pattern. A regression sits deliberately on the low twitch end. It is a touch off on average because the world is not perfectly straight, but it barely moves when the data moves. On a small or noisy table, that trade is often the winning one. The fancy model's flexibility becomes a liability, not just an edge. Now, the other side. Because the tabular story has genuinely moved, and I will not pretend otherwise, the version where the simple models always win is out of date. A recent benchmark called tabular-data found the gap has closed. And a newer kind of model is moving fast, one called TabPFN, from a company called Prior Labs. Is trained ahead of time on millions of made-up tables, so it predicts on a brand new table in seconds with no retraining. It started out only on small tables. Its newest version now lands tables up to about 1,000,000 rows. So I'm not telling you regression wins. I'm telling you something narrower and more useful. On everyday tabular data, the simple family stays competitive with systems that cost far more to run, and the burden of proof still sits with the expensive option. For a method this old, that is a remarkable place to be standing. So before you decide regression is what you graduated from, look at what is running your bank, your hospital, and the network you thought replaced it. What I would actually do is measure how often your expensive model beats the plain one on your data. I do not know what you will find, and I would want to hear it. If this changed how you pick models, the full write-up is on my Substack. Let me know in the comments below what you think, and I'll see you again soon.